Okay. So now we're going to get into the anatomy of how you would encode a memory and make a memory. So, or rather store a memory. So I'm hoping that when I was showing you the examples before of the aplysia, that you were appreciating that there can be different components to a memory, and that in some ways, something that is activated at the same time might encourage the strengthening of a connection, right? So if we move to the mammalian structure of the hippocampus, I'm going to first show you the kind of fine detail of this anatomy so that you can have a sense of the type of circuit that would be involved in the formation of memory, but also so you can have an example of different ways that you could form a different connection. So I showed you the example of the aplysia before, which had the axon terminal and then actually an axon terminal connecting to that same axon terminal. And so it actually strengthened the signaling power of that first connection. And that would be a presynaptic connection, a presynaptic learning. So if you have the synapse being the space between two neurons, you have the presynaptic neuron and the postsynaptic neuron. Presynaptic is the one that's sending signal into the synapse, and the postsynaptic is receiving information from that signal, right? So you can have any variety of type of enhancement of a circuit with these different elements of a synapse. So all of that actually exists within the same structure, the hippocampus, that's responsible for encoding and ultimately signaling memory to the rest of the brain. So we're going to talk about these different parts of the hippocampus, primarily to talk about different types of memory that can take place. So for instance, classical synaptic transmission memory would be LTP, long-term potentiation. So in this case, the example that I'll give is this Schaefer collateral pathway, which is signaling from a part of the hippocampus called CA3 to CA1. And this connection here, if you are to stimulate it, which is what's indicated by this little electrical coil, this is a stimulation. And then if you record from activity in this region where the CA1 neurons are, what you'll see is that if you give a high stimulation, that you can then induce a stronger response over time. So this is our baseline response. It's at 100%. You then give a really strong stimulus, which is called a tetanus. You just kind of buzz the signal quite a lot over a short period of time. And then you go back to just giving a little bit of stimulus again, and you'll see that you have sensitized this connection. So whereas it was at 100% before, after that little tetanus, you can get it up to 150 over the period of 30 minutes or so. So now you have multiplied it by at least 50%, the sensitivity of this signal. And we know the mechanism that it's through an NMDA receptor, because if we give a specific drug called APV that blocks NMDA receptors, we know that we can block this learning mechanism. So the NMDA receptor is quite an interesting little protein. It is always blocked. It's always got something in it, actually a little magnesium ion that blocks the flow of information in and out of that channel. Except when the neuron is already depolarized, then the magnesium will come out and then information can come into the cell, right? And so what you would call that is a coincidence detection, and you'll hear much more about this later on. But a coincidence detection of two things happening at the same time is essential for many types of memory. So you can imagine that that is essentially what's happening with the aplysia, is something happening at the same time at the siphon and the tail. It's what happens when you have the instance of Pavlovian conditioning. So this sort of detection of two things happening at once is critical in order for a connection to be made. And so an NMDA receptor is a really nice mechanism for how the brain can detect a coincidence, because what it means is that you have a neuron that's already excited and another signal comes in at that same moment. because the NMDA receptor will only respond when the neuron is already excited. And so that means it's primed to accept another connection and strengthen that connection. And that is the sort of memory that takes place at this connection. You can then also have connections coming in to the CA1 from a direct route that could require NMDA receptors, but also require calcium channel. Basically, we don't need to get on the details of that, but this is just another example of using different drug cocktails in order to actually determine the mechanism. So this is actually a causality test. APV is not sufficient to block this memory, but APV plus a drug that blocks this channel is sufficient to block that memory. So it's a combination of those two receptors, or those two channels, that actually allows for that memory. And then the last example is the mossy fiber input along this into the CA3 area. And this is our presynaptic memory. So this memory is only formed by the production of new proteins in the presynaptic neuron that encourages more release of neurotransmitter. So you can either have a postsynaptic change mediated by something like NMDA or NMDA plus a calcium channel that allows for more detection of signal, or you can actually have an increase in the amount of signal that is sent, right? So those are kind of the two basic mechanisms for how you could change a circuit. You could either shout louder, or you could listen better. Those are essentially the two ways, because you always have a call and response of a neural pathway. Yeah. So you'll go more into these details, I believe, soon. But these are mechanisms for how you could increase the sensitivity of a connection. That this is the type, we believe, the type of mechanism that's taking place within the hippocampus in order to encode an experience that could be turned into a memory. Now, the memory, based on work from, obviously from HM and other work, we have a belief that the hippocampus is not really storing that long-term memory, that it's somehow offloaded to other parts of the brain. So the hippocampus is here, and all of the other parts of the neocortex connect to the hippocampus, give input and receive input from the hippocampus through various routes. But then you could have all these other spots within the cortex that the hippocampus could then spread that information to, right? In a very similar mechanism, actually, to how the circuits are enhanced within the hippocampus itself. So the general model for how this might be done is here. And this is where I will allow Mario to be more specific if he would like to. But the concept is that your encoding is done within the hippocampus by enhancing signaling within the hippocampus and allowing for associations to be built. And then you have pathways out of the hippocampus to other associative cortices. You can have a short-term retrieval of memory before it's properly consolidated purely within the hippocampus. So this would mean that you could have a short-term memory. HM would not be able to do this. Or you could have a really long-term retrieval, which means that the memory has already been fully offloaded into the cortices, and it now exists within a network that's extra hippocampal, that only exists out here. So if you were to destroy the hippocampus, any memory stored within this type of framework would still be available to us.
Yeah. So if you want, I'm going to comment on this slide.
Yes, please. Yeah.
Can you mute yourself so that we don't get that?
Oh, yeah, definitely.
So the difference between the short-term storage and the long-term storage, I think, is really fundamental here. And we do believe that there is a combination between the neural network activity and the activity of the secondary molecular cascades, and also of sleeping. So our current computational modeling of these of the long-term storage and retrieval, they don't have anything close to this level of detail. But the understanding of how associative networks, such as recurrent neural networks, as you see in A, is basically our makes the core of our understanding of how memory encoding works. You basically are driving a set of networks that represent the sensation and perception, potentially also older semantic memory, that are all being activated in interesting sequences or so forth and so on. And these sequences, they are played during experience and replayed later during sleep. And it is believed that they will then promote this more perennial encoding. So it's an interplay between the short-term activation with the long-term resonances, if you like, at the level of cortex. And these have been converted into models to a certain degree, and I would like us to talk about it when we're going back to recurrent neural networks, models of encoding of attractors, such as the Hopfield network. And clearly, one of the main learning rules that we discuss is the Hebbian type of plasticity, right? So the essence of any associative learning is things that happen together are more likely to be together. Now, there are a lot of network specificities that Hebbian doesn't, in this big umbrella doesn't include, such as it's not like everybody excites everyone and then everybody connects, because then in the end, be a big blob. You do need some more contrast and more specific circuits to be responsible for specific elements of that encoding. So they will have the semantic circuit, and you don't want it to be completely associated with other circuits. You want they to operate sort of independently. And so these cortical modules idea, I think that it's what many experimenters and theoreticians believe to be a good representation of the system we have. The specifics of the process are being spelled out as we go, and we don't have, like, I think, the final model for memory encoding and retrieval, although we have many little components that play together. We will go back to Hopfield networks later on in the course when we talk about recurrent neural networks and about Hebbian learning. You guys cannot see, but just outside of the window, we have the window cleaners going up, which is a bit disruptive. Yeah, I feel like the seeds of that process are understood, and that's at the level in which we're going to be discussing this later, also computationally. So I think that this is a perfect continuum between what Josh is telling you and what I'm going to be telling you later. I'll mute myself.
Okay. Yeah. So then, if we have, I think what's important to remember is that these connections that are taking place within the hippocampus follow these rules, these different learning rules, and they are existing at this level. So obviously, this is a single neuron. This is a single neuron example in this schematic, but this is full of many neurons that are all interconnected all the time. And they are capable of forming these recurrent networks within the hippocampus, but then also send signals outside of the hippocampus to the cortices in order for the memory to now be held somewhere else. And so you create these recurrent networks outside the hippocampus that was fed into by the hippocampus. But the question exactly is, what is really the mechanism? Is it that you have this recent memory where the hippocampus is telling the neocortex all the time? You then have a remote memory that's held only in the neocortex and doesn't require the hippocampus? Or do you have this multiple trace theory where you have the hippocampus telling the neocortex in the beginning what's happening, and then a buildup of a kind of a guided buildup of the network outside of the hippocampus afterwards? So I think this is still something of an open question. This is now, we're moving into the realm of the theoretical. But this is the type of neural network that exists in your brain in order for long-term memories to be stored. Okay, so that is all to say that you have these different types of synaptic plasticity events within the hippocampus that can lead to the strengthening of certain signals that allow for a more sensitized response to a specific input. So I'm going to give you an example of what that might look like. So this is now at the synaptic biological level. So if you go from, for instance, the CA3 neuron to the CA1 I showed you before, that is a NMDA mediated learning process. So here is your little magnesium block that's in the way of the NMDA receptor. But you also have an AMPA receptor, which is also a glutamate receptor that allows for sodium to move in and out, potassium to move in and out. That is always present on the membrane to some extent. And the NMDA receptor is available in order to allow for also calcium to pass through. So calcium is a very significant signaling molecule within the neuron, but essentially it's a little bit of a bonus signal that further encourages the production of protein and the insertion of new channels in the into the membrane in order to increase the signal. So this is an instance of listening better, where you don't actually need more glutamate to be released in order for the signal to be strengthened. If the neuron is activated in a way that the magnesium block is removed from the NMDA receptor, it is now open and calcium can come in. It then activates this intracellular pathway that then sticks more AMPA receptors into the membrane. You actually have more ears now with which to hear the glutamate that is released. So these are the steps of LTP. And the way that would look in a recording scenario is that you could stimulate cell A and record from cell B. You can then elicit LTP in a variety of ways. We don't need to get into all of them. You have before LTP, essentially a silent synapse where the AMPA receptor is not actually in the synapse. And after LTP, you now have an unsilenced synapse where you can actually signal to AMPA even without the NMDA receptor being activated. So before LTP, you have no change in the EPSC of cell B. We can now check to make sure that there's actually NMDA receptors present, and you have a little bit of a current induced by the NMDA receptor. And then after LTP, you now see this EPSC. So this tells us that there's actually now AMPA receptors present because we activated the NMDA receptor, which allows for the increase of a connection between two neurons within the hippocampus. So I'm going to show you an example of the hippocampus being involved in a specific type of memory formation now, and that would be spatial memory. And I'm going to tell you what that is. So the question is, how can you study memory in an animal? And specifically, how can you study spatial memory in an animal? I need to fix my audio settings one more time real quick. Okay, so does anyone have any familiarity with spatial, what spatial memory would be? And then if you do, with how you might test that in either a human or an animal. Does anyone have any concept of that? What would I mean by spatial memory?
Spatial memory for an animal can be like seeing if the animal still remembers where you hide some food or something. Or for humans, it can be mapping or knowing directions. Do you also asked how we can test it? Okay.
Yeah, exactly. But that's exactly right. And then, yeah, how would you test that? Does anyone have an idea of an experiment for how you might test that, either in human or an animal? Let's see, who should I bother? I'm going to bother Kansu. Do you have any ideas?
Yeah, I was actually thinking an example that I think Ms. Bandra gave a few lectures ago, like maybe that can be a type of an experiment, but basically there was just like mice in a labyrinth, and if you can like moderate that experiment, like change that in a bit to test spatial memory, you would like you'll insert like a high diffuse in one labyrinth, and after a few trials that mice can learn, like mouse can learn the directions to find that if you put it at the same place, so that it sort of can have like a cognitive map of that place, like a spatial map, and then maybe something like that, but I don't know. That was like the fastest example I could think of.
No, that's a great idea. So hiding something in space and then testing if the memory or if the animal can find it is exactly right. So in the example you gave is it was food. The example I'm about to give is a platform in a pool of water. So in this case, you put a rat into a pool of water that the animal can swim in. And just beneath the surface of the water is a little platform where the animal can actually stand to no longer have to swim, but he can't see it above the water. He has to remember where the platform actually is. So in this case, what you can do is you can also give the animal clue or little cues around so that it can kind of position itself in space. And eventually, after day 1, day 2, day 3, you see that the path they take gets shorter and shorter to find the platform. So this would be an example. So something like this with a hidden compartment with food would be the exact same process. Eventually, after some process, the animal would learn where the platform is or the food is, and their route is the readout here. So the fact that it takes much less time to get there would tell you that there's a spatial memory being formed and maintained. And then what you can do is you can test to see how long they spend in a place, so how strong the memory is by removing the platform. So here the animal will swim looking for the platform and there's no longer there, so they will spend a lot of time in the quadrant where the platform is. And you can then begin to reverse it and put the platform in a different area. Now, what's interesting is that even though this is in a completely different place, you'll find that the animal learns much more quickly to find the new platform because they no longer have to learn even the concept of the fact that there is a platform to look for. They now just have to learn where is it. And so now you can really directly test spatial memory by actually moving the platform and then having the animal relearn where it is. So this is a Morris water maze. Sometimes people used milk in order for the water to not be clear. So definitely the animal could not see the platform. And so you can just imagine those poor researchers that had to reach into a bath of milk and pick up a rat that has just been swimming in milk. That's a sort of care that goes into these experiments. And then the other thing that you can do is you can just move these cues around. And if the animal is using those to navigate in space, you can actually completely disorient the animal by shifting them maybe 90 degrees or 180 degrees. So that they no longer know the same way, the same placement in the space, and they actually would run in an opposite direction, for instance, if you shifted everything around 180 degrees. So in this case, this Morris water maze, we know that there's something involving LTP in order for that to be done, because, for instance, if you interfere with the expression of NMDA receptors. So you have your CA1 neuron here that is expressing NMDA receptors, and you might have some sort of mutant mouse, for instance, that has no NMDA receptors. In that case, you cannot induce LTP in the physiological recording, and those animals do not learn the same escape latency. So here's an example of a wild type animal that finds where the platform is. And here's an example of a mutant animal over multiple days trying to find it and just swimming around aimlessly. So essentially, here is the, if for instance you have 4 quadrants, that means that there's a 25% chance that the animal would just discover the platform by chance. In the wild type example, you see a much higher than chance performance. And in the mutant example, you see always right around chance. So this means that there's something within the hippocampus that is taking place that requires LTP in order for the animal to learn this task. Okay, so this sort of spatial memory is first encoded in the hippocampus and maybe maintained in the hippocampus. It's kind of interesting to think about. But I'm going to show you now an example of that through the work of 3 people who actually quite recently won the Nobel Prize: John O'Keefe, Maybrit Moser, and Edward Moser. John O'Keefe first discovered place cells in the oh no, 1970s, I want to say. They believe it's the 1970s. And then many years later, the Mosers discovered grid cells. And then in 2014, they shared the Nobel Prize for the positioning system within the brain, is what it was called. Okay, so what did they actually discover? John O'Keefe discovered that if you place an animal within some space, so here you call this an open field, it's just like a cylindrical space, and then you record from neurons within the hippocampus, you will find that there's actually a place field, some sort of element within that space, within which the neurons within the hippocampus will fire more. So let me show you a video so that you can really understand what I'm talking about. In this video, here is the rat right here, and we're going to track it in space. So you have a square box, quite a large box. This is a scale bar for a meter. And we're just going to let the animal navigate this space, just walk around. And then what you're going to see is a line that's tracking where the animal is moving. And then you're going to see these little red dots appear. And those red dots are appearing whenever a neuron within the hippocampus fires that we're recording from. Okay, so I'm going to press play. And it might have a little bit of a lag to it, but you'll still be able to see the trace. Here on the other side is actually the neural recording. And what you can see is that as the animal moves around, the neuron is firing throughout the space, but it's preferentially firing down here in the bottom left quadrant. So as the animal moves around, you can really start to appreciate that there's a preference in space that this neuron has. So this would be then that neuron's place field. So there's neurons within the hippocampus that have a tuning curve for a position in space. So this is in 2 dimensions, of course. So this is a place field that's developed in 2 dimensions. Recent work in the fruit bat, I believe. It's some species of bat.
Yeah.
I can't remember which bat it is.
I don't remember if it's fruit bat or not.
It's a type of bat, but it's a lab in Israel, I believe,
Sure.
published a 3-dimensional place field and grid field map in bats, showing that creatures that fly are also developing these sorts of maps of space in 3 dimensions. So people have tried this in rats by having them climb over certain obstacles. And you can see that there's a 3-dimensional element, but obviously there's nothing quite as 3-dimensional as flying. And those creatures also develop this map. So this is a place cell. This is a neuron within the CA1 region of the hippocampus that ends up firing preferentially for a certain space. But we also have that other half of the Nobel Prize, the Mosers, discovered grid cells. So here is the same sort of thing, another square open field and the animal moving around here. And we're now recording a different part of the brain called the entorhinal cortex, and we can watch what that neuron does. I think we need to pick up the pace a little bit. They're going to speed up the video soon, hopefully. Yes, okay. So as the animal moves and moves and moves, each one of these dots is actually now the firing of one neuron within the entorhinal cortex. And in the beginning, it kind of looks like a mess. It looks like it's just firing everywhere. And by the way, the researcher on the right there is dropping food pellets into the open field so that the animal will keep moving around, hunting for food. With enough movement, you can see what's actually forming here is a grid pattern. And so what you see is this hexagonal pattern, and that is the characteristic organization of a grid cell. So what you see is that the neuron will fire along this hexagonal organization, you can see here. And in theory, grid cells feed into place cells. And we believe that because of the actual anatomy of where these are kept. But first, we're going to talk about the theory of that a little bit. So one interesting element of grid cells is that different neurons within the entorhinal cortex will fire according to a grid, and they will fire according to a grid that spreads out in space. So certain neurons will have a very tight grid where the spaces between them is very small, and some neurons will have a very wide grid where you have a hexagonal map that is meters long. And by combining all of this information, you can actually feed down onto neurons within the hippocampus to develop a singular place, for instance, where that neuron fires only in that one spot. That's the concept. So for instance, if you have a map 1, they can actually feed down into one neuron and create a place here. You could have a different map, same neurons, and they actually develop a different response to a different place, and they end up developing firing in a different spot, okay? So grid cells, I told you, are in the entorhinal cortex, which is this area here, and they feed directly into the hippocampus, which is part of the development of this theory, is the anatomy actually comes in, and here you have both of these pathways, and they ultimately feed onto the neurons in the CA1 of the hippocampus, which is where place cells exist. So the same way with the loss of the performance in the Morris-Water maze, if you disrupt LTP, you actually disrupt the formation of place cells. So here's a wild type mouse. You have a neuron that prefers this upper right quadrant of the open field. If you inhibit LTP, you see that on a session by session basis, there's no clear development of a place field in the firing of the neurons within the hippocampus of these mice. Okay. So this is the theoretical framework of place cells. I'm hoping there's a concept that's already beginning to pop into your head as you have this number of neurons feeding onto a neuron, which is then firing preferentially to some sensory input. The sensory input here being kind of a high concept of place, of where you are in literal space. Okay, but we'll get back to that in a second. I'm going to first show you the other option. So you have LTP, which is a potentiation of a signal, but you sometimes may also need to turn down a connection and weaken that connection. And that would be through the process of long-term depression. So you have long-term potentiation to increase, long-term depression to decrease connection. So here, for instance, you can do the same thing. You can actually mediate it also through the NMDA receptor. But if you stimulate at a very low frequency, you can actually induce the endocytosis, or the removal from the membrane of AMPA receptors, and actually turn down a connection. So LTD, if you give a certain type of stimulation, actually leads to a decreased response from one neuron to another across the synapse. If you lose LTD, you don't necessarily lose the ability to find the hidden platform, but you do lose the ability to quickly revert to a new place within the Morris-Water maze. So here, for instance, is the learning curve of 2 different mice, the wild type in gray and the transgenic that has the loss of LTD. And you see that they have a very similar learning curve in order to find hidden platform 1. But then when you suddenly move the platform here, you have more instances of the animal going to the original location than you do in the wild type. So the wild type here is learning more quickly. When you remove that transgene, you actually see the same sort of learning curve. So it's a very brief change here, but you see that the loss of LTD decreases your flexibility a bit in order to learn something new, right? It will do many other things, but this is just an example of the type of contribution that LTD has to behavior. Okay, so these are now the kind of neural mechanisms for how a memory could be formed, stored, and changed. And I just wanted to give you some real examples of how that would actually happen in space. So in any given room that you walk into, you're also going to form a place map like this. It'll take you a minute. So once you walk back into a room that you're extremely familiar with, you feel very comfortable. You could probably move around your own bedroom in complete darkness. You have a very good understanding of where things are, of where you are in space. But if you were just dropped into a completely different room, you would feel very disoriented if the lights were just suddenly turned off. You would have to feel around. You'd have to get a lot of sensory input in order for you to actually navigate around the space. So you first have to learn where everything is, and that map can actually be stored or at least maintained. It's difficult to say exactly with spatial memory if it's entirely offloaded from the hippocampus or if it's always stored in the hippocampus, but it can be at least maintained in the hippocampus. Okay, so I'm kind of getting to another, let me see. No, we can do a little bit of this. We might end a little bit early today, I'm not sure. But okay, so we've now been talking about explicit memories that are mediated by the medial temporal lobe, more specifically hippocampus and terminal cortex. So these are events and facts. They can also be space or your knowledge of where you are in the world, as we've seen. But there's also the implicit memories. You might say that this is what the Aplegio is going through, was the implicit memory of associative learning. And we can also study associative learning and other implicit memories in mammals. So one example of that is, of course, eye blink conditioning within the cerebellum. So this is a kind of a very simplified summary schematic of what eye blink conditioning looks like. This is a publication from our department a number of years ago. It's a very nice paper. I recommend looking into it. And essentially within the cerebellum, you have the Purkinje cell, which is able to pick up a huge variety of sensory inputs and ultimately can associate two different inputs in order to mediate a response. So in this case, the conditioned stimulus is a little flash of light in front of the animal. And the unconditioned stimulus is an air puff to the eye, which reflexively leads to an eye blink. And with some training, you can actually teach the animal to blink now to a light. So this is your neutral stimulus. There's no reason that this should lead to a blink. There's every reason that an air puff to the eye should lead to a blink. And after training, the animal can predict the air puff to the eye just with the conditioned stimulus. And that requires an actual change in the neural circuitry. That means that the neurons that are mediating the eye blink now need to become sensitized to the conditioned stimulus. So the way that looks in practice is that you can record from neurons within the cerebellum. This is a coronal section of the cerebellum. The recording site was right here where they were recording a Purkinje cell. You can give a light stimulus here, which is passed through the visual cortex and then communicated through the pontine nucleus into the parallel fibers of the cerebellum, which ultimately signal to the Purkinje cell. And the air puff is actually communicated through a different pathway that ultimately converges onto the cerebellum, meaning that they can interact with one another within the Purkinje cell. So you can actually end up combining these very different signals, a light flash and an air puff to the eye, within a single neuron, such that this will now teach the animal that this is coming, right? So in this case, this is a naive animal, and this is the air puff to the eye. And what you see is a strong firing rate following the air puff. After training, you now see the same sort of response to the CS. So this is the actual neural mechanism that would take place in order for you to learn to associate two things. And this is happening so quickly, this is only 250 milliseconds, that trying to do this consciously would be quite difficult. So to some extent, you need the implicit memory stored within the cerebellum to get the timing right. So if you want to blink just before the air puff is coming, you need for some sort of circuit like this to detect these two things are associated in time. So I'm including this slide, even though it's way too complicated, and I apologize. But this is a really interesting paper. I think it's a great one to check out. It's one of my favorite papers from recent years. And what they did was they performed eye blink conditioning, and they actually tried to detect how a series of movements might be learned, because obviously eye blink conditioning is just the activation of a singular movement of the eye, and then that's the end of it. But what they thought was, maybe in order for a series of movements to take place, one movement can actually drive the next. So if you imagine the complexity of a serve in tennis, for instance, you have to imagine the number of muscle activations that have to be produced in the correct organization and timing in order to ultimately hit that ball. And if you watch a tennis serve of a professional tennis player, it will be almost the exact same every single time. It's incredible, actually. If you track the movement, it's so consistent in a professional tennis player, which means that the brain has learned really precisely to activate muscles in a very accurate way. And so the theory in this paper was that you can actually use the internal processing of producing one movement to drive the next movement in a sequence of movements. So here what they did was they trained animals to produce a conditioned response of an eye blink to actually drive the next eye blink. So what they were doing was giving a light flash and then a little air puff to the eye to drive the eye blink. Eventually the animal learns to blink from the light, and they actually can then use just the sensory feedback of the blinking itself to drive the next blink, so that they can see a sequence of blinks like this. So the sensory feedback from blink 1 drives the second CR and even sometimes a third CR. And the timing is so precise that we know that it's actually being driven by the same feedback. It begins to fall away because the feedback is not as strong as the initial teaching, but this is in theory how you might learn a sequence of events, is by using the sensory feedback from the first part of the movement to feed into the next one. A very interesting paper, I recommend it. So check out the citation down here. Okay, so we're gonna take another break now. And for the next part, we're gonna kind of get more into more of the definition of memory and how it might be stored in the brain. But I hope you can appreciate the neural mechanisms, how you create a memory, and the ways that we actually record and study memory. But okay, so we're gonna take a break now, and we can meet back again at 11. So I'll see you all then. Okay, let me see. So now that I've filled your head with more details, I want to make sure that we step back and keep in mind the overall goal here, which is to understand what memory actually is and what learning is. So I want, again, to have a discussion with all of this in mind that I've told you today of what is a memory. So I'm going to bother Ruud. Can you just tell me, keeping in mind what you've heard today, how you would describe what memory is?
Yeah, I'm really sorry, but my Wi-Fi hasn't been working whatsoever
Oh, no.
today. So I've only picked up maybe
My father helped me.
1/3 or something.
Ah, that's a shame. But do you have anything today that has updated your definition of memory? Oh, I think you muted yourself again. You can type if you need to. It's up to you.
No, it's fine, but I didn't understand because my dad was talking to me.
Oh, that's okay. But is there any of the third that you heard? Is there anything that has updated your definition of a memory, or any additional way that you would think about it?
Well, if you sorry, I find it kind of difficult.
It's okay. I'm going to give anyone else an opportunity to say if they've updated. I see Neba.
Yeah, I would say that memory, it has different forms. First off, there's different kinds of memory, and it is kind of the storage of information, either that be like long-term or short-term or working memory, and it can be in different regions in the brain, on different ways. That's how I would easily like try to explain it.
Yeah, exactly. And I think one thing that's good to keep in mind is that even though we have different types of memory that may be mediated by the precise neurons that are involved in that memory, but the actual mechanism of how the circuits are enhanced or decreased could be very similar between these types of these regions of the brain. And so therefore, you could have a very different type of memory. You could have a procedural memory versus a semantic memory of just remembering some fact, but the actual mechanism for it could be quite similar. It could be something like an NMDA mediated LTP, or it could be the storage of proteins within a neuron. So there's actually quite a lot of similarity, even though we have these different types of memory. I'm trying to think if there's anything else I want to discuss before we move on to the next bit. Oh yeah, so did anyone have a memory themselves jogged when I was talking about the grid cells feeding onto place cells? Did that remind you of any previous thing that we've discussed? This is quite an open-ended question, but if that was reminiscent, I would be curious. So if you have the place cell that is responding to a certain space, and you have multiple neurons that are feeding onto it, how would you then describe essentially the firing of the place cell within the hippocampus? Any ideas? Do you even get what I'm driving at? Is it too vague?
Yeah, well, I'm not quite sure actually.
Yeah, so if you remember, let me see, how can I say it without already just giving you the answer in the question? So what I'm hoping to drive home is that there's quite similar mechanisms of building a response of a neuron, very distinct from the exact sensory input that neuron is responding to, right? So you have to ask yourself, what is a place cell within the hippocampus, a neuron that fires within a certain place? What does that then tell you about that neuron? its response is then there. So there's a certain buzzword that I guess I'm driving at.
Like a tuning curve,
Exactly.
like that.
Yeah, exactly. So I showed you the classic tuning curve is the visual neurons that are responding to bars moving in space, and they're responding to a certain direction. But a tuning curve can be incredibly complex. And a place cell is essentially the building of a tuning curve that is tuned to a certain position in space. So it's always a little simpler to talk about the visual system because we can literally see it and we can imagine it quite simply, and we're visual creatures, so it's easy to conceptualize. But all of those dynamics are existing in every system within the brain. You have neurons that are responsive to something, and they are responsive to something within usually a Gaussian distribution, some kind of level around it, and they are usually being fed onto by a convergent system, which I believe, has convergence already been covered, or is that later?
A little bit.
Okay, so then you have grid cells that are converging onto a single neuron within the hippocampus and helping to build a rather complex tuning curve. So it's not just seeing some shape in some orientation, it's actually knowing where you are in space. And so you have to think about all of the things that go into that. It's your visual awareness of everything around you. It's your knowledge of your body moving in space. If I move from here and I have a place cell firing to here and I have a place cell firing, that means that I needed to detect my own velocity and my own movement across that space, as well as seeing the shift in the visual field, as well as feeling the shifting of my body as I actually move my body around. So you have to imagine all of the things that are going into building this very complex tuning curve that is a place cell. I just wanted to keep that in mind because the next thing I want to talk about is more of the concept of what a memory is itself. So there's this term in engram, which is a little bit of a tricky term to imagine, an engram, because it kind of makes you think that there's a physical piece that is a memory. I'm reminded of the movie The Never-Ending Story, but that might be showing my age and my Americanness, so I don't know if everyone will appreciate that. But in the Never-Ending Story, there is a part, and maybe it's even in Never-Ending Story 2, I can't remember, but there is a part where memories are just being selected out of a bowl and destroyed, as though they are these just singular physical things. And that's not necessarily the case. An engram can give you the false impression that there's just like a piece of your brain that is a memory and you can zap that part of the brain and that memory will go away. I don't want to give you that impression, but there is, to some extent, I believe there is a Never-Ending Story too, to answer your question, Julian. So an engram is a unit of cognitive information, and this is quite hand-waving, I'm hand-waving on purpose here, that is theorized to be the means by which memories are stored and their biophysical or biochemical changes in the brain. Now, I also want to remind you that there is an interactive element where certain neurons have to then fire in a sequence sometimes in order to end up with a memory. But there is obviously these biochemical and biophysical changes. Sometimes receptors need to be stuck into the membrane to make the listening of a postsynaptic neuron more sensitive, or you have to build more protein in the presynaptic neuron to release more neurotransmitter to shout louder. Or there's actually a combination of things, and then there are even other options as well. Those are simple options. But these are the sorts of things that can exist within the brain that could be a memory in itself, right? Okay, so not to kind of overdrive the point there, but I don't want to give you a false impression. So yes, I wanted to remind you of this tuning curve element that Kansu remembered with me. So in this case, of course, you have the neurons that are responsive to movement in different directions. But the example I gave you before was really quite complex, of the example of my Mexican Korean food truck. Really delicious, I missed that truck. But that is a complex memory and a combination of things. And it requires presumably some convergent input of different types of information. And so I want you to imagine how you could end up with, oh, I just spoiled it by hitting my mouse. All right. How you could end up with a neuron that is responsive to a combination of these things. And maybe if you read very quickly what my next slide says, you might already know. But imagine what must take place in order for you to build a tuning curve that is a combination, for instance, of Korean food and Mexican food. Does anyone have a mechanistic explanation of how that could come to be? Any ideas? Who has not spoken yet? Laura, I don't think I've heard from you in a while. Do you have any ideas?
Well, I read Hebbian learning on the next slide.
Oh, you did already. Cool.
Yeah.
Yes. Oh, you read Hebbian learning. Sorry. Yeah. So anyway, so I spoiled my answer. Yeah. Terrible technical issue there. So yeah, so I spoiled the problem. But something like Hebbian learning could produce that, right? And so you can imagine that in the hippocampus, when grid cells are coming together, there's a lot of grid cells that are detecting information in different parts of space within the entorhinal cortex. The entorhinal cortex is receiving information from the visual cues all around you, as well as your self-motion information. And actually other information you could use. Animals, for instance, use a lot of odors in the air to detect where they are in space, if they remember where odors are. We're not quite as odor driven as mice or rats, for instance. So we probably wouldn't produce a odor map of a space, but like a dog might, for instance. They might go into a dog park and they may not have something of a map of space based on smells that they can pick up from different areas. But you have then neurons that are detecting all sorts of different information and converging onto a neuron that is a place cell that knows where you are right here, right in this space. And so you have a neuron firing here. But that means that you have to pick up all this other information. And the only way that that neuron could have a tuning curve like this is that you have information, for instance, from the visual cues of a rose and the odor of a rose. That would lead you to a rose neuron that would fire in either case. This neuron is going to fire when you smell a rose or when you see a rose, or even when you conceive of a rose and you imagine one. You might have a neuron that would fire that way. But the only way a neuron like that could be created is to have inputs from different sources coming together and firing together. And when this one fires, you might imagine that it depolarizes the neuron, it activates the neuron. Magnesium block comes out of NMDA receptors on these synapses. And then this is also enhanced, this connection here, right? So then you have a neuron that when this pathway fires, it actually to some extent imagines this pathway. So you can actually have an association of very different senses to come up with a conception, because this neuron is ultimately going to feed into something else, into the next thing. And when this neuron fires, the next neuron doesn't necessarily know if it's because of you smelling the rose or you seeing the rose. It just knows that a rose neuron has been activated, right? So this allows you to now have a conception in your head of a thing, regardless of how you might have gotten to that thing, if that makes sense. So Hebbian learning is unsupervised. You've already probably talked about this, or if not, you will talk about it quite a bit more. So you should understand that you have different inputs coming in and different weights of those inputs, and then an ultimate output neuron. And the way that these can be formed is vast, right? So we're not going to get into the exact circuitry of Hebbian learning or the neural network element of Hebbian learning. I'm going to show you some examples in real life of things that could change these weights. So for instance, you have emotion, attention, association, or repetition. These could change these weights. So if you think back to the rose example, if you have some memory of your mother having roses on the table as a child, that might help to enhance the connection you have and the ease with which you might create a rose neuron, because you have that emotional response or you have that memory in your head. And really, at a mechanistic level, that means that you just have more neurons that are coming together to fire at the same time, right? That would be the actual biological mechanism with which an emotion could lead to a stronger connection forming. And experience you certainly have had, and I believe, I don't think we're all old enough yet that this wouldn't do something. So this is an example of a flashbulb memory. And you probably already know what this is. And I may have even already triggered your memories of the exactly where you were on this day and how the world might have changed or whatever. But 9/11 is an example of flashbulb memory. And it's because it was such an emotional state that it actually can be written very, very strongly into your head. So I have a really strong memory of exactly what I did that entire day. And imagine if I just said, okay, well then what happened on September 12th of that year? I have no idea. There's no memory of it, right? But I have a really strong memory of this whole day, even things that are unrelated to it. And partially it's because you need to remember when something is a very strong emotional response. So imagine if, okay, we're going to go back to very old memories that we actually don't have, but imagine that you are now hunter-gatherer on the plains and you go to a space and your brother gets killed by a tiger right over here, right? You're going to remember that place now, and you're not going to go to that place anymore. You have a very strong emotional response of that. And this is the same sort of circuitry being tapped into here. You're activating your amygdala, which then feeds into your hippocampus. You're activating your, presumably your serotonin and dopamine systems, which can enhance the formation of synapses. These are all the mechanistic ways that an emotion could change the formation and the maintenance of a memory, okay? So one example of something like that is the dopamine system. So this is a reward pathway, and dopamine you might think of as being like a pleasure signal. It doesn't necessarily have to be a pleasure signal, but it could be a pleasure signal. It might be better to think of dopamine as a salience signal or even a motivation signal. For instance, in Parkinson's disease, when dopamine neurons are dying and it's inducing tremor in Parkinson's, it can often also lead to emotional dysfunction and especially motivational dysfunction. So people with Parkinson's disease are not as likely to have the will to do things anymore, because dopamine can actually drive the will by giving you an expectation signal, right? So the way you get to motivation is quite a high concept. So you have to kind of break down the components of that too. The way you would be motivated for something is that you would expect a reward to get it, to happen, right? So I'm motivated to stand up right now and go to the coffee machine because I know the reward of getting coffee, right? But I have to first get up, I have to stop what I'm doing. That can be kind of a bother. So you have to have enough motivation to stop what you're doing, get up, use the energy to walk away, find a cup, press a button, all in the expectation of the ultimate reward. But if you don't have a properly functioning dopamine system that tells you the reward, you may not have a motivation to actually go do the thing, right? So the way that actually looks is, if, for instance, you have a cue that produces a reward most of the time, or rather actually here. So if you have a cue that produces a reward very rarely, a probability of 0.01, the reward will release some dopamine itself, right? But this cue is not predictive. So the cue won't give you anything in terms of a dopamine hit by itself. But if you have a cue that gives you a reward 50% of the time, you have a little dopamine response to the reward. You actually will learn to have a dopamine buildup over time, and you'll even have a little dopamine hit just from the cue. If you have something that produces a reward 100% of the time, you almost don't even need the dopamine hit from the reward. You get all the dopamine hit from the cue. But if you suddenly don't get a reward from the thing that is 100% of the time inducing a reward, you will actually feel the pain of having a reduced dopamine flow. And you'll actually feel a negative response, right? So this is the sort of circuitry that takes place. This is the VTA, which is an area that contains dopamine neurons. It signals to the amygdala, giving you the emotional response, and to the hippocampus. And dopamine can actually be can encourage synaptic formation, and it can encourage synaptic enhancement. So that's the way that this sort of reward system could be built, is by the signaling of dopamine. And so that means that all of these different inputs have to go into the dopamine signal for you to perceive of something as being connected in time with a reward, right? Okay, so that's the way that an emotional experience can change memory, and this is the rough mechanism of what that would be. There's also attention. Now, attention is even more complicated, and I'm not going to try to get into too much of the explanation of the machinery behind attention, but I'll give you an example. This is also linked with motivation, but motivation can encourage you to pay attention in different ways. So in this experiment, subjects are shown different images, either food images or non-food images, and the subject is either hungry, they skipped lunch, or they just had lunch. In the cases where the subject is hungry, they remember the food images more likely than they remember any of the other images. And if the person is non-hungry, there becomes no difference. So the mere fact of being in the state of being hungry and feeling motivated for hunger can actually increase your attention to something that is a food memory or food image to such an extent that the memory will be stronger. So that means that there are signals ongoing that are increasing your focus here. This may be a dopamine signal, this may be a serotonin signal. It's actually enhancing the formation or the strengthening of synapses such that your recall later on is easier. Yeah? Okay, so this is a difference between, or this is how attention could affect your memory. Could be driven by any number of things. This is just an example of that. Another way that your memory could be increased is through the association with the previous experience. So first I'm going to show you this example, and then we'll try to think of other examples. So this was an experiment where chess players of different skill levels were shown images of chessboards. I am not a chess player of significant enough skill level to detect that these are necessarily gameplay or random pieces, but I would imagine this is a real gameplay scenario. And then this is just a set of random pieces. So what you can do in this experiment is show an image of one chessboard and then ask people to remember where all the pieces were on the board. Quite difficult. If the person has a very strong skill level in chess and they are presented with an image of a real scenario that could happen in a real game, they're much more likely to remember it than if it's random or if the person has a low skill level like here, right? So when you have a low chess skill level, you have a difference in the ability to recall them, but it's not as big. But if you're really skilled in chess, you immediately would imagine this game scenario, and it makes it easier to remember it. So this is an association with a previous experience. It allows you to kind of add it onto your previous knowledge and update your knowledge, and it can kind of work into the normal circuitry of your memory, right? It's, to be honest with you, this chess example I thought was so good. I have a hard time coming up a really solid analogy for a more realistic scenario, but if anyone has a good example.
Something occurs to me.
Yeah.
Let's see if they come up with something.
Well, I have the black
Medicine-
pawn on the
medicine
8th rank I would definitely remember. So that's interesting.
Medicine to have like a reaction in which like she might actually have something to say.
Oh yeah. If yeah, so if anyone has another okay, so someone just noted, are you talking about this pawn here?
Yeah.
No, like the upper one.
Like in the 8th row, like together with the white queen on the right side.
Oh, right. Oh yeah, you're right.
It would already have changed into something else.
Yeah.
Actually, there's one in the 1st row and the 8th row. Both of them don't make sense.
Yeah.
So good point.
Yeah. So it's interesting to imagine that.
May I try one?
Yes, of
So
course.
I don't know if you can hear me. Can you hear me? It's a bit yeah, sure. I'm using Josh's microphone. On the topic of things that don't make sense together, right? It's like you have some expected patterns to
Yeah, yeah.
There was this experiment on cerebellar relationship with mirror neurons,
Oh, interesting.
in which they presented tools being used out of context. For example, I don't know, a drill being used, a power drill being used to brush your teeth, you know, and the reaction times for cerebellar patients to judge what was basically a non-functional scenario were much longer. So basically they didn't see that that odd combination, that pattern that was not fully consistent. I
That's
forget what
interesting.
the exact examples are, but there's something with a broom. So is a broom in a weird scenario? For us, a broom should be, you know, close to a bucket that will clean the room.
Yeah.
But the other one has a broom on the desk. I don't know.
No, that's a great. You're reminding me now of those stock photos of just like people doing weird things, and like there's a whole series of women just laughing with bottles of water and drinking them poorly. And I'll never forget those because it's so strange to see. It doesn't make any sense. But you're exactly right. So obviously these chess scenarios are very specific. But you obviously, if you see something that makes no sense, it's going to stand out in your memory very strong.
So yeah, someone with a chicken hat,
Right.
you know, in an everyday scenario.
Yeah, that's
I mean,
really
the
fun.
odd one out.
Yeah, yeah, exactly. Well, so
But
it's
that wouldn't work
complicated
because
actually. Yeah, it's almost the
yeah.
opposite. But yeah, it's interesting to imagine that. Maybe the emotional element would be part of that. But yeah, I think it's really funny to imagine the mechanisms of those different responses there. Like why I remember those because they made me laugh. Maybe that's the emotional response.
Expectation. So I think that the best theory that I have ever heard about humor was that humor is a violation of expectation with no cost for the subject.
Oh, that's a good point.
So that you would, in German, for example, Schadenfreude could still work as humor because, you know, if someone else sleeps on a banana, you know, no one died.
Right.
Or even if someone dies, it's someone you should like, and then you find it funny.
Oh yeah, that makes sense.
If if the 21st century doesn't make you think of that as always inappropriate.
Right.
But yeah, well, I'm always inappropriate.
But I mean, obviously, the women laughing with the water bottle, they got paid, so that's fine. They're not hating. But yeah, that's very
Do you guys have any other example that you would like to contribute to this? It's a conversation, right? So the idea here is that you have a context, and that context is also somehow encoded in our expectation context, and like our experience contributes to what is our expectation and how we basically can encode things in our memory.
Yeah, I thought maybe language. If you have like, for example, you ask a person to remember a bunch of words and you have words in different languages. And if it's maybe like similar or emotional or something, they might remember it easier than if the language is very different from their mother language. So like, if you would ask me to remember Chinese words or German words, I'll probably remember the German words easier because they're closer to Dutch.
That's very good point. Oh.
Yeah,
no, that's a great example. Very nice one. Yeah, I think, and I think I was thinking of an additional one that's so simple, which is that everything that I'm telling you today, you might remember more easily than someone who's never sat in a classroom at all before. So you already have like the associative memory of being told something and knowing to remember it. And it could be even that basic. Like you've already gone through a whole lifetime of sitting in classrooms and talking with people and listening and knowing that you will need to know this for the future. But if we just took someone who had never sat in a classroom before and plopped them onto this Zoom screen, imagine the number of things they have to learn at the same time that they're learning what I'm telling you today. You know what I mean? So associative memory kind of allows you to skip the baseline the early hurdles of making a memory and jump right to the immediately important part. And so, yeah, the German Chinese example is a great example. And it's why I always feel badly if I can't remember names in languages that I'm not as familiar with. So I always write them down and take them more seriously when I'm told those names, because I know it will be more difficult to remember them later on. So you have to increase your encoding in order to help with your recollection later on. But yeah, that's a great example. Does anyone else have a possible associative learning example?
Yeah, I actually have a question about your Zoom example. Because like, since we are experienced students,
yeah,
wouldn't you also say that like we probably remember less from your lecture than someone that doesn't have experience here? Because we have experience that we need to listen to specific things, and the things we need to remember is basically the bottom line. So not every word you say, but only the conclusions you say. But someone that doesn't have experience in the classroom doesn't know which specific things to focus on. So they might actually remember more like overall information, what you say, than we do. Like we probably remember more of this important things, but through associate learning, we might only pay attention to the important things. So
I understand what you're saying, but I think it's because if you don't know to filter what you're experiencing through some sort of associative memory, then your focus is so scattershot that you may end up remembering nothing at all. So I think you're right that someone who has no experience might also be noticing the stuff behind me more often. They may be noticing my inflections of how I speak. They might not ignore all of that. So there's a lot of things that you're ignoring in this moment because you understand the scenario that you're in a different way. But all that stuff could be distracting as well. And so even though they could be taking in a lot more information than you are, because it's all new and novel, it could end up completely destroying the memory of a lot of the other components of what's happening. So I agree that that's indeed a possibility that they could end up remembering more, but they could end up remembering almost none of it. It could just be a blur. You know what I mean? So I think you could imagine the scenario where a novice sees this and they take in all the information in a way that a kind of a professional would not take in the same amount of information. But because it's so much and so overwhelming that they actually have a difficult time remembering as many things, even though they take less for granted. You know what I mean? So I think it's possible, but I think the attention is a really important part of forming proper memories and really putting things in context and putting them in the framework of your memory. Yeah, so I'm going to show one more way in which memory can be affected, and that's a very obvious one, I would imagine, to everyone, is just repetition. So when you're studying for a test or when you're just going through life, the fact that you remember some phone number is probably because you've dialed that phone number many, many times before. So you've just repeated it over and over again, right? And so if you practice for a long time, you could remember a span of digits up to 80. I mean, there are people who can go really deep into pi, for instance.
Yeah, indeed. Can I add something?
Of course, yeah.
Do you guys remember Brainscape? So the principle of delayed repetition, of repeating something at the right time, should allow you to know even the digits of pi if you put them in flashcards. So I think that a normal person that is just confronted with the idea of remembering numbers, and just they give them cookies or something, so that they have a valence to remember, they will remember up to hundreds of digits of pi, a normal person.
Oh, yeah. They could, but it would take quite a lot of repetition.
It will take quite a lot of repetition.
But then also the fact that you're saying cookies is important. So I'm giving you these things that are components of how you might enhance memory or learning, but obviously they're all working together. So even the person who would on their own sit and try to memorize pi, there's a motivation there. And to some extent, that person might be really motivated to impress all their nerdy friends that they work with, for instance. There could be that sort of, so Mario has up to 10, 15. to me, and he has just impressed me. So he already gets the reward of me being impressed. So that motivation exists for his memory. But then also repetition is essential. You can't, you wouldn't be able to do this without repeating it and thinking it over and over again. And you have to think about what is the actual mechanism of that happening. That means that those neurons are being activated over and over again. And those connections are being made that are really solid. And the response then to the sequence will become more and more easy over time. So as you think of 3.14, the next one will be triggered by that internal mechanism more easily because you've activated it more often. So you can grow, yeah, exactly. So you can grow the sequence that you remember by activating it over and over again. So repetition is important, but it's interrelated with all of these other elements, these attentional elements, these associative memory elements, and motivation
And
elements.
here it's also obviously good to remember what is it, when you mix together colors and sounds, you are a
Synesthetic.
synesthetic.
Yeah.
I mean, like synesthetic persons are known to be, associating melodies with numbers or colors with numbers, and then suddenly they remember many more digits.
Exactly.
So
And I imagine to some
big
extent
storage
there's like a
space.
spectrum. I don't know if there's like a binary of a synesthetic person. I think probably we exist all in some spectrum of synesthesia. And
Yeah,
there's some people that just have it in a really intensive way.
yeah, I
And
agree with that.
it becomes almost a difference of kind at that point.
Yeah.
But yeah, I mean, you might associate some number with some color or some number with a certain letter. So it always would pop into your head, and maybe it makes it easier. There's also like the what's it called? The memory palace mechanism, where you kind of create an imagined space in your head, and you put different things into that space, and it allows you to create a story. And a narrative story is actually a way that humans are potentially unique in the animal kingdom. And that's how we remember things very well. We remember things in a sequence and a narrative. And if you put something that you need to remember into a narrative, it makes it much easier to remember. So that's So that's a method that you could use for memory, and it's just taking advantage of the way that we remember things.
Yeah, and I think it's also in this context, right? Remembering how episodic memory and semantic memory relates to space.
Mhm.
So I think that it's an underappreciated fundamental fact of the hippocampus that it serves to encode space, but also episodic memory.
Yes.
And so somehow, like this metaphor of having space being promoting like storage, you can bring the two together and put some episode inside a room, and it becomes easier to remember. You think about going to that room, and then you know what the episode is. So the memory palettes like bootstraps on the idea of spatial memory.
Exactly. Yeah, I'm trying to think of like so a lot of the ways we imagine remembering something is we create a visual memory, because that's typically how we experience the world. We're very visual. But we also talk about movement, and we talk about space quite a lot when we're imagining memory. And I'm literally blanking on good examples of this.
Prepositions, I think, right? So in general, if something is on or in or under, I mean, like some of them will be easier to remember than others.
It's all relative space.
Relative space.
I think I have maybe a good example for this one.
Yeah.
Like, remember the vocabulary test on in high school, where you get a whole list of words and you have to learn all the words and what the translation is. And if you would say you give a few people the same list 10 times every time, and the other people you give the same words but in random order 10 times, the one with the first list will remember more things, because they associate the words underneath each other with each other, because they've seen it so many times. And the other ones, it's random, so they can't really associate the words with each other.
Yeah, it's spatial. Yeah.
Exactly. Yeah, that's a great point. And it puts it in a context that makes it easier to remember the actual thing that you're focusing on, without all the other stuff that you might have to remember. So any new order or any new, like, imagine if you had some random combination of words and it sounded strange to you, and that is actually can be distracting. Whereas if you have a real familiarity with the list, yeah, I think it would make it easier to remember the individual words, and you would almost remember them all as a piece. But you would still know that they were different components, and you would still be able to select the individual words. So yeah, that's a great point. Okay, so I'm going to finish.
Julian had also a point, and since this is an interesting discussion spectrum, I mean, did you, Julian, or was it my impression?
Did he? Oh, you mean he just?
Yeah, I don't know. Maybe it was just I'm reading too much into his behavior. Forget it. Let's move on.
Okay. Okay. So we're going to close a little early today on an example from some interesting papers. So we're going to try to show. I'm going to try to show you some examples in the literature of how we know these things to be. So, for instance, fear memories. If you remember my example of the tiger eating your brother over here, that fear memory it can be associated with a space very easily. So certainly, if I know that in the middle of that field there was a tiger, then I will remember the context that fear memory existed in. And that has been tested in animals using a foot shock approach. So you give a small little bit of voltage into the metal floor that the animal is on, and then you test them for freezing behavior. Basically, if you give a little foot shock here in this context, and then the next day you put them back in that context, they will already freeze, remembering the foot shock. So they will, just that context itself will produce the fear memory, and they will recall that they were shocked there before. If you inject a protein synthesis inhibitor, you will find that, oh, where am I? Here. Okay, so if you inject a protein synthesis inhibitor before you give the foot shock, then you'll actually not see any freezing in the animal, because they will not have produced the new neural material in order to strengthen synapses, make new connections, in order to actually form this memory. So this is an example of the physical proof that there are actually neural changes going on in order to encode a memory to recall it later. So if you put the animal in this context, inject a protein synthesis inhibitor, give them a foot shock, test them the next day, you won't see them freezing, and you won't see an example of the memory. Okay, so the question is, can existing memories be also modified in this sort of way? So what I've been talking with you a lot about today is updating memories. And part of the reason for that is that whenever you're kind of imagine getting into a memory, you're activating the neural circuits again, which means they're now somewhat fragile, because you've now opened it back up to an extent. So if you, for instance, give a foot shock on day 1, and then give them a protein synthesis inhibitor on day 2, the question is, what will happen on day 10? Does anyone have an idea? If you test them later, if you give the protein synthesis inhibitor on day 2, well after the day 1 foot shock,
the memory will not get reconsolidated because it doesn't.
Well, so in this context, the animal is just given the protein synthesis inhibitor just in their home cage or completely outside of the context of the box. So on day 1, they're put in the box and given a foot shock, and then day two, they're given a protein synthesis inhibitor. So in this case, there should be no association between whatever neural circuits are being inhibited here and the original memory. So in this case, the test will result in the animal remembering the experience. But if you give a protein synthesis inhibitor in the context of the box on day 2, you can actually disrupt the memory on day 10, meaning that it's actually, as they remember, it's fragile. And so you can actually disrupt subsequent recollections. Okay, so we're going to close on keeping in mind that this is the case, that you have actual neural circuits that are activated in order to elicit a memory. How would you create a fake memory? Does anyone have any ideas? No, not very much, actually. I should incorporate that more into this, but
When you mean create a fake memory, you just mean so there was no experience and then the animal thinks there was experience, or just it has a sensation that it has an experience.
yeah, yes, exactly.
So maybe it has learned something and then you activate the network responsible for that memory and then it feels that it is re-experiencing.
Yes, very nice. So we don't need to get into the, well, maybe you can imagine the technical ways that you would do that, but that's essentially what you would do, is you would activate a network that is producing a memory that the animal didn't actually have. So this is a now fairly classic study from Tonegawa. I recommend checking out this paper. It's in Science. It's quite short. It's very dense. Of course, it's a science paper, but it's not too long actually, and the explanation is fairly clear. So creating a false memory in the hippocampus. I'm going to explain to you the basic way that they did it. What they did was they used a driver called CFOS. You don't need to know the exact thing behind that. You just need to know that CFOS is activated when a neuron is really active. So what they did was they used CFOS as a driver of channelrhodopsin, which is an optogenetic tool, which the expression of channelrhodopsin allows you to activate neurons with light. Yeah. So they put the animal within an experience just in a box, and they allowed CFOS to drive the expression of channelrhodopsin. And then on the next day, they put them in a different context. So now in like a square box, for instance, and they gave them a foot shock. But they also activated the neurons from the day before optogenetically at the same time. So to some extent, they paired these irrelevant neurons with the foot shock neurons. And then ultimately they could make the animal remember that this was a negative experience by just activating them again with light, because they've now paired them. So the memory really should be this foot shock situation, but instead they've now made the animal think that this was a negative experience by pairing the neural circuits. Okay, so it's an oversimplified schematic, but this is in the paper. So this is how you might create a false memory. And the reason I bring this up is to remind you that a memory is a certain activation of neurons at the right time in response to the right stimulus in a well-coordinated way, right? That's essentially how a memory would actually exist within the neural circuitry. Okay, and so that allows you to do the next thing. So this is a subsequent paper where they were able to switch the valence of something. So valence is when something is positive or negative. So you can think back to now my cookie or skunk example. Positive valence for the cookies, negative valence for the skunk. And what they wanted to do was to teach the animal that a bad thing was a good thing ultimately. So they have a fear engram here by activating the amygdala. And they have a reward engram, which in this case, what they did was they either, for the fear, they gave a foot shock, and for the reward, they allowed the animal to hang out with an animal of the opposite sex for a little while. That was the rewarding part of this study. And what they did was same basic premise as the previous one. They activated the expression of neurons using CFOS, and then they optogenetically stimulated them. And they were able to get animals to remember the foot shock when they saw the animal of the other sex, or to remember the animal of the other sex when they were in the context that gave them the foot shock. They were able to switch the emotional experience that the animal had with the memory by activating a different circuitry. So these series of papers were really important to understand what an engram actually would be in the brain. So it's not a little glass ball like in the never-ending story. It's a set of neurons that are activated at the right time and in the right way. And in order for those memories to exist, they have to first be encoded, which means that the sensation must be felt. They need to be run through the proper circuits. Those circuits need to be strengthened or weakened in the right way. And that way, when you feel that sensation again, it activates them properly and you remember it. Or you can even trigger your own memory by just conceiving of it and activating the neurons in the right way. And that is essentially the memory. But the actual mechanism is the neural network that delivers it along that pathway, right? Okay, so that is essentially all for today, but we have plenty of time. So if anyone wants to discuss anything in more detail, or we can end a little bit early, it's whatever.
Yeah, I think a little bit of discussion makes sense to me because
Yeah.
many of these things that we've discussed today, memory is one of the most complex discussions in the realm of neural-based cognition. And when we're talking about modeling memory, there are many interesting aspects. For example, now you know that you need a protein to model memory, right? To model fear memory, you need a certain protein. So how does that relate to spiking, for example? I'm just thinking that there are many interesting questions that we would like to unpack here and that you might want to unpack.
Sure, yeah, so, yeah, exactly. So if you imagine, so really, if you really think through what's happening with these last couple papers where they were able to create a false memory or switch the emotional valence of a memory, remember that those neurons are ultimately have the tuning curve for that really complex experience. So that complex experience of being put in a box that had a foot shock in it, there's now neurons in your brain that have a tuning curve in response to that sensation, which means all the different elements of that experience had to converge onto a neuron that holds that memory, or a neural circuit that holds that memory, maybe a little recurrent network that holds that memory. And so here, what you can see is sets of neurons in the amygdala or in the hippocampus that are getting all of that input together and then are activated in response to that input. And the fact that you can just activate them in this very artificial way, this optogenetic way, means that you're bypassing all of the convergent inputs onto that neural circuit and creating the false memory by jumping ahead of all the sensation that feeds down into those neural circuits. So that's how I would think about the network that would feed into a memory and what a memory actually is.
Yeah, I agree. No, Mace at 1109 asked the question, how do we quantify engrams? Did you notice that question?
I did miss that, sorry.
I think it's a very important question. As we get to that, I wanted to add that we by now have also created the memories via electrophysiology in the hippocampus. We, during the night, so during the day, we measure the place cells.
Yeah.
And during the night, we activate the same place cells that have been used and that are known to be encoded in the hippocampus. On the next day, the mouse will go there where you've activated.
Mm-hmm.
So you will have a preference, you will display a preference for being in that location, even though there's no reward associated. So basically, mouse goes into big maze, encodes the entire maze into place cells. You, as experimentalist, selects one or two places. During the night, you reactivate some of those cells, and in the next day, the mouse prefers that place.
Yeah.
Whoa!
Right.
I mean,
by just increasing that circuit.
Yeah. So increasing that circuit for the encoding and then using that. So the emergence of the engram, the emergence of the fear engram, the emergence of the location and preference engram. So, and just to finish my contribution here, Josh and I were discussing after the first pause in today, how is it? What are the learnable things?
Mm-hmm.
You have a very fat channel of information that you're submerged by. And yet the things that you can learn, they feel like object-like, logical, a piece of thing. One number, another number, binding the numbers together, right? So the sequence of number, they're abstract on the one hand, but on the other, but on the other, they feel like rather object-like. So how do we transform the unstructured stream of experience that comes to us through the statistical regularities of the environment into sort of a logical level that allows us to talk about it, talk about events, talk about procedures. I mean, these highly abstract notions that encompass the structure of the reality that we humans see that is not in the world. We made them and we learned them. And so I think that even before we are, able to learn and specific set of numbers, we somehow have the ability to encode numbers. And so that's, is that nature or nurture?
Yeah.
What do you guys think?
I think it's just our ability to think in abstract manner. That's how we're able to encode numbers.
Yeah, so what is our ability to think in abstract manner made of?
I think nature, yes, I think. But you can never say like nature and nurture, obviously, that's always the answer. But if the ability, I
what's
think.
the difference between us and a mouse?
Oh, yes. Nature.
Right. I mean, so be careful when we have these polarizing opportunities. So it's a dichotomy, it's a false dichotomy, surely, like you pointed out before. It's hard to really settle on a decision. But it's the same as the question by Mays earlier, which I think is very proper. How many n-grams? How many n-grams can a brain encode?
Oh, is that the question? Oh boy. Yeah.
How do you quantify them in the first place?
Yeah. Yeah. So actually, Mace, how do you feel about these experiments in terms of your question about quantifying n-grams? Sorry, I missed your question before.
Sorry, what exactly do you mean by that?
So the examples that I've shown you now, the past couple papers where they were testing for instance, freezing behavior, or testing for a preference maybe for a space that has a rewarding experience. How else would you quantify, or is that the sort of quantification that you were thinking?
Yeah, well, for me, an n-gram was explained as a unit of cognitive information, right? But it just what exactly is this unit? That's a little bit vague to me. And also, for an n-gram, for example, how do we decide which neurons are important enough to be included in that n-gram? And because it's also interconnected, that's there's a lot of room to play within, right?
Mm-hmm. Yeah. So I mean, I think your points are maybe discussion level. I don't have great answers for them because to some extent I wanted to keep an n-gram vague. I don't want to make you think that an n-gram is a nice little package that you can just find a protein in the brain and oh, that's the memory, because it's really a complex, actually ever shifting set of neurons acting in the right way. There's actually these drifts that can take place over time where you can feel like you're having the same memory, but it's actually a slightly different subset of neurons that are holding that memory over time. So it can kind of be moved around in different networks. So you should look up the
manifold hypothesis.
Yeah, so you can look up the manifold hypothesis. You can also, what's the drift? What's the term I'm thinking of?
Drift.
Yeah, I guess just drift.
Neural drift.
Yeah, if you look up neural drift, that's a fascinating world where we can watch how different populations of neurons actually become responsible for holding a similar memory over time. And the question of what is the right set of neurons that are responsible for the memory is really difficult, especially because you want to maintain flexibility. So we talked about this a little last time when I was teaching. You want a circuit that is robust enough to do the thing that it's supposed to do, but flexible enough to also be modified. And so to some extent, if you had a really rigid set of neurons that were responsible for one memory or one behavior, you would lose some of the flexibility that allows us to learn as easily as we do. So the fact that you have a bunch of neurons activated that may or may not be critical for that memory is actually important for that component. Does that make sense?
That makes sense, yeah.
But I would really recommend checking out some of these other things that we're mentioning here, because it's intensely complicated, but it's fascinating. But that's why I want to simplify it enough to make it clear in this amount of hours that we're talking about it. but it's not even this simple. It's even more complex than what I'm showing you today.
Yeah, I mean, like from the modeling perspective, there's also a couple of insights we can cast. Particularly, there is one powerful metaphor for how a memory is encoded in the brain that I'm going to be bringing more and more often to you, which is the notion of attractors. But not now an attractor in the context of a limit cycle attractor that produces a spike in an index neuron, but a larger scale attractor in a recurrent neural network. So we're going to be discussing, what is encoding capacity in neural networks, and then you will be the judge as to what extent that encompasses what we believe that memory is in our brains. Now, while on the one hand, I think that the problem is semantically and philosophically kind of it's difficult because it is not well it's not easy to pose, right? So, right, we're just talking about what is an engram. But on the other hand, I mean, if you think about object memory, right? So the fact that we know what a t-shirt is, there is a semantic spectrum around a t-shirt. There is fabric, what it's made of. It has a hole for your head, the same way as a chair, you sit on top, and it has more or less the size of a human. So these kinds of requirements, these kinds of conditions for something to be something, I think that they could be thought of as being encoded essential features of something. Now, how does it become an essential feature in the brain? I mean, partly it goes back to the question of what have we been rigged to recognize as possible usable objects in the world, right? We evolved through 4 billion years to also use the world and the environment in specific ways. The ways in which we can interact with the environment probably help us tessellate, really tile the world in the things that are meaningful to us. And I think, personally, that these sets of features that create the semantic space of objects, basically what objects are made of, are kind of nature into us. That requires nurture, clearly. So if there's a nature part that is rigged to self-organize the stream of experience in ways that feel like objects. Whether objects exist in reality or not is a philosophical ulterior question. But that we come rigged with apparatus, with a neural apparatus that help us organize the world in ways that are meaningful to us, I think I'm completely convinced. And now I'm going to blow your mind away by saying that I think Hebbian learning and recurrent neural networks are a phenomenal way to model these types of self-organizing processes that acquire structural regularities to represent specific things in the world. Now, to the extent that we haven't the perfect recurrent neural model of the brain that can do what we do, the way we do it, with all the capacity and flexibility we have, I think that we have small beginnings. And these small beginnings can give us metaphors that allow us to construct our understanding. The engram, in that case, the engram in the amygdala is a set of neurons that has a meaning. And that meaning has to do with that experience and with everything that has been used in that time. So just to bring us together with the notion that we're putting together the experience plus these networks plus the fact that we have this endowment in ourselves that has this uncanny ability to acquire the universe within our time scale, time and spatial scale, right?
In our dimensional scale.
In our dimensional scale. I mean, we were talking about the embodied brain last week. I feel it's very important to put ourselves in a body to look at things. Mm-hmm. If you had a disembodied set of retinal receptors, they could never make sense of the universe. They have to be close to each other. So there is nothing like a disembodied mind. There's only an embodied mind, and that's the only way in which it can reciprocally define what is meaningful in the universe for it. this is a little bit of a
Yeah.
philosophical tangent there, but it's just it's the way that I like to think about if we're ever putting something together from what we have.
But I mean, they must be connected with each other, because it's actually, the memory can be held in the actual connections between them, and not necessarily just in one neuron.
Exactly, it's relational, right? So when you build your own receptive field in the project, you know that you select which neurons receive stronger weights. You know, the way in which you connect the retinal sensors to the output neuron that will have the receptive field for vertical bars. The important thing is that the neurons that are arranged vertically in the retina have stronger connection to the one upstream. Yeah. So it is sort of like this relational construction that allows the selection. Yeah. How things are put together.
Cool.
Comments, ideas?
Any other questions or thoughts?
I think the discussion that you were having about this organization of different concepts and how and exactly in which manner they get encoded, would it be possible to, because the impression that I got and what I also think is maybe functionality of the item, for instance, or any concept might be the most relevant, its most relevant feature that to which we're able to relate to it and to see it's within the context, macro context. So like, would it be possible to arrange some kind of cognitive or, I don't know, physiological experiment in a way that we see how the semantic organization in a real organism of different items who share functional characteristics, how that would happen, so that maybe that would answer the question a little bit.
So across different organisms. You mean across different organisms?
Yes, as well, might be, yeah.
Or I thought you meant like within a neural pathway, maybe. Or am I misunderstanding as well?
What I meant is that functionally proximal things, how they would get encoded, and would it be possible to some kind of decode their encoding? But
so I think in a single brain.
In a single brain crossover, in any way that might be possible. Is there a way in general?
Yes, everything, fMRI, EEG, electrophysiology, everything can get you a little bit closer to it, wouldn't you think?
But a little bit less, a little bit more precise than, like, I know fMRI, but isn't that too general overview?
I think
imaging,
we will,
look
to
at
some extent,
population.
I think we'll to some extent get to this with the functional topography, because on the next couple courses next week, we will walk through the experiments that you would do and the results of experiments that would allow us to follow the encoding of a sensory experience within the brain. So I hope that will be satisfying. That will be satisfying for the question that you have there, if I'm understanding it properly. But we will see.
Yeah, I feel like Mariam is also thinking a little bit about, how can we get better? I mean, like we have like a first level approximation of many of these ideas. Yeah. And say for instance, a chair, right? What is a chair made of? What is the essential elements and essential neural elements of a chair? Yeah. I think that it's important to think about this. And actually, this binds with the one announcement I had for today. So if there are no more questions, I wanted to make an announcement about, you might have even already stumbled upon it. So in Canvas, I put up an announcement about the night of the BCI. I want you to read it as well, Josh, afterwards. Okay. So the night of the BCI is the 22nd of October. So we have decided that in order to crown your experience of the computing brain, we will have an evening session. So the BCI session is going to be broke into 2 sessions. That has to do with the fact that Sadaf couldn't make to the actual time where the BCI lecture was scheduled. But then we started creating a universe here of ideas about what this awesome night of the BCI is going to be about. BCI, for those of you that do not know, means brain-computer interfaces. The idea is that we have to start discussing what is encoding and what is decoding of the brain, and how many things can you encode, how many things can you decode. But we're going to be using very specific paradigms of modern existing BCI techniques that we will unpack in this session. The session will be broken in two pieces. The first piece is you're going to watch some videos and find your groups to work together on an explanation for the crowd of what your BCI method achieves. And we're going to have some specific requirements for you to, some learning goals, if you like, for those particular presentations. And have a read about the Canvas notification announcement. If you have questions, ask me either per email or in Canvas, Teams, everything works. And I think it's going to be really fun. At that day, we're going to have from 6 to 8, we're going to have some pizzas. We're going to have some soft drinks sponsored by my lab, and then we can discuss brain-computer interface. And if the weather is fine, we're going to be doing that in a terrace. We're going to be projecting these lectures and talking about it in the outside, in the great outdoors. It is the 22nd of October,
right.
From 6 to 8. That's the idea.
And that morning is the introduction of the journal.
And
clubs,
the morning of the BCI is the first part of the session is I think is on that morning too. I have to just check.
Okay, I thought that was when we began the journal club component. The 22nd.
So it's the last lecture before the journal club.
Okay.
That's right. So it's on the 20th. The 20th is the first session. First BCI session is on the 20th, and on the 22nd we will have the actual night of the BCI. And our first session of the journal club is on the 26th of October. That's when we.
Okay.
26. Questions? Comments? Suggestions? Feedback? If there's nothing else you want or need from us, I'll see you tomorrow with the synapses and ARM, and we're going to review project 3, talk a little bit about spontaneous activity in neural networks, and then criticality and cascades, attractors, and all of these fun things. All right, cool. Okay,
Good to see you all.
so guys, see you tomorrow.
Yep, see you next week.
Thank you so much. See you tomorrow. Bye.
Bye.
You.
Have a good time.
Thank you.